working as professor at Manit Bhopal, and sir has over 20 years of teaching and research experience with 3 years of industrial experience. Sir specializations are in energy management, power electronics and drives. Sir has published a total of 85 publications, and sir is a member of IEEE Fellow, Institute of Engineers India, Fellow, Institute of Electronics and Telecommunication Engineers. Sir is also the life member of Indian Society of Technical Education, life member of the System Society of India, and sir has received the postdoctoral research at École des Technologies Superior ETS Montreal, Canada during the year 2016 and 17. Sir has guided more than 6 PhD scholars and 23 MTech students. Sir is also the consultant for research projects on position sensorless control for PMBLDC motors under research promotion schemes of AICT New Delhi during 2016 and 2013 to 16 at SLIET Longwal. Today, sir is with us to give us a talk on microgrid configuration and control. Sir, it is our privilege to have you. Over to you, sir.
Thank you very much. I hope I'm audible to all of you clearly.
Yes. Yes, sir.
Okay. So I'll start with my presentation, and it is on microgrid configurations and control. Is it visible to all?
Yes, sir. Yes, sir, it is visible.
Okay. So, as you know, at present, microgrids are very much preferred in many of industrial, commercial, and I can say utilities installations. They are preferring this kind of configuration. I'll just go one by one. Usually the microgrids are designed for renewable energy extraction, and then to utilize that renewable energy at the local level, it is being used. So to discuss a bit of renewable energy scenario in India, if you see the renewable energy scenario on 31st December 2017, this is the data given by the ministry. You can see here the wind power is having a larger chunk in 2017 as compared to solar photovoltaics, and other small hydro, biomass, biogas or bagasse generation, and then waste to power. It is having very small chunk. If you see in 2018, you can see that solar photovoltaic has increased very drastically.
Excuse me, sir.
Yes.
Sir, only the first screen is now visible, sir. Have you moved this slide, sir?
Yes. I have moved it. Just a minute. I'll just try once again. Okay, I'll just start with the complete screen, then maybe.
Yes, sir.
Now it is visible, sir.
Yes, sir.
Okay, just check whether is it changing?
Yes.
Slides are.
Yes. Now it's
okay.
They are changing, sir.
Okay. So if you see from 2017, here you can see solar power very small compared to the wind power. But the next year, if you see, it has gone to a very large chunk. And in 2019, if you see, it is almost comparable to solar photovoltaic and wind power. Both are equal, almost. That means during these 3 years, 18, 19, and in 20, the data will be available I have not checked it out, but it is almost comparable to wind power. If you see even figure wise, 37.09 gigawatt of solar photovoltaic and 31.69 gigawatt of wind in 2019. That means solar photovoltaic has exceeded the wind. It is because India and Indian government, they are investing much more on solar photovoltaic, and we are almost going to be the largest solar power producer. So with this scenario, if we see, there are many things which will come up. As a researcher, if you see all these areas, then definitely you are having a lot of things to do. Capacity addition of 27.07 gigawatt of renewable energy during last 3.5 years. And the components, you can see the solar, wind, small hydro, and biomass. So solar and wind are going one neck to neck in the capacity addition. If you see the targets, what the government has targeted, basically the government is targeting to have a lot of projects in this area, and the solar PV installation dominating almost 48% share of the total capacity installed in last years. And out of this, the government is focusing more on rooftop projects, solar rooftop projects. That means domestic installations are going to increase. That means each household or each commercial installation, like our institute is also having that kind of installation, we are utilizing our rooftops, and those rooftop installations, they are coming, and in future they are more, they will be definitely coming more. So India is planning to have a lot of projects, and as well as these rooftops, the government is planning to have the bulk power generation, like 35,000 kilometers square area of Thar Desert marked for solar power project, and they are going around 2100 gigawatts there. So that kind of scenario will be there, apart from water pumping and other accessories which we are using for solar power utilization. So government has set an ambitious target to achieve 40% of cumulative electric power through renewable energy by 2030. And maybe if we are going by this pace, definitely we will be achieving this before 2030. So the targeted areas are solar and wind. Now, if we have such things in our system, how we deal with them? This is some of the examples. Bigger power projects like solar power projects, solar parks in different parts of India. Now, how we use this solar energy, I'll just have a small glimpse of those things. Solar photovoltaic, as we all know. Then there are solar thermal systems, solar cooker, solar water heater, solar concentrators, air dryers, and heating, ventilation, and air conditioning systems. Now, why solar photovoltaic system was not popular earlier? The reasons are, first, high cost. So when we got better technology for cost cutting, it is now coming up. Then it's weather dependent. We know that if there is cloudy conditions, we cannot get anything. So if we are having a weather dependence, and if there is a power demand, how to meet it? That will be a problem, and we can't change with it. Then a requirement of battery storage. If we want that the power which is to be used can be stored later on, or we can say that the solar power is available only in the daytime. What about the night? Because most of the loads, lights, and many things are in the night only. So how to compete with that? So for that, we need battery storage. And for that, we are coming up with some new applications or smart grid applications, or some alternative measures where we can avoid the battery storage, because battery storage cost is almost equal to solar photovoltaic panel cost. That means if we are installing a solar photovoltaic panel and if we are installing a battery, it will be double the cost of the solar photovoltaic. So we are trying to avoid it so that the cost can be reduced. And then low voltage DC generation. Usually we are having AC applications or AC appliances in all our domestic, commercial, and industrial systems. It is a standardized norms of 230 volt or 400 volt in 3 phase. But the solar photovoltaic is generated at lower voltages. And if we want that it should be at higher voltage, we have to do series and parallel connections. So there are requirements of multiple connections. There are requirements of converters, like we have to use boost converter or any special device so that we can match with that voltage. And these are certain reasons. Then we have one more application. If we are having, let's say, low voltage generation, some of the persons are working on a DC microgrid that is also in low voltage DC microgrid. So if you are going for low voltage applications, we have to standardize it. Like if you just remember a few years back, we were having these mobile phone battery chargers. Lot of phones, means different companies, they were having different types of chargers. If you are having say Nokia phone, or if you are having Motorola phone or any other phone, you cannot use the same charger with the other phone. But now they have standardized it. The similar problem comes with the DC. There are different DC voltages and there are different applications of at those DC voltages. So until we standardize, like if we are going in the market at present, and if you say give me a bulb or give me a fan, there is no need to tell what should be its voltage level. We know that it's 230 volt 50 hertz AC supply. So all the voltage, all the accessories or devices, they are standardized to that only. But if you see for the DC, it is not standardized. Some you may get at 12 volts, some you may get at 20 volt, 24 volt, 48 volt, like that. So there is a requirement of low voltage application, and that is to be standardized. Then the requirement of controllers. At present, solar PV systems, we are having requirements of controllers. We are having normal 220 volt or 230 volt appliances. We need to control the charging because there are requirement of charging control for the batteries, for the storage. Then power quality control in grid connected system. That is very important, because when you connect a rectifier and a charging in between, there are different measures of power quality, like power factor is poor, the total hardening distortion increases. So peak factor is increasing. So those things are to be considered. And then maximum power tracking. This is very important, and many of the solar PV systems, they are having. Basically, we say that whenever the renewable energy is available, we should extract it at the maximum possible power. And that gives us this feature, maximum power tracking. So there are two methods usually the people are using. One is called mechanical tracking, other is called electrical tracking. Mechanical tracking is about keeping your solar panel perpendicular to the solar radiation, and electrical tracking is following its power generation curve. So I'll discuss those things, and most of present systems, they are having this. So if we have, we summarize what are the R&D challenges with solar photovoltaic systems. We have maximum power tracking. This is one of the challenge, how to get it. Then storage cost minimization, controller reliability, then development of applications suitable for solar photovoltaic system. This is related to the DC applications. Then system behavior under certain changes of solar irradiance. Suppose suddenly cloud comes, or there is a partial clouding, and a lot of load is there, how your system will behave. Because we say that when solar photovoltaic system is there, there is no inertia in your system. Suddenly it will become zero, suddenly it will become very high. So there will be a problem of stability in the system. Then control of power flow. So these are the things which are to be covered. Then if we say controllers for the solar photovoltaic system, we have already discussed these 3-4 areas: 220 volt appliances, control for charging of storage, control of power quality, then maximum power tracking for all kinds of converters. And we are talking about the electrical converters or electrical power point tracking. So we use boost, buck boost converters for that kind of tracking. Now, maximum power tracking, we have two, mechanical and the electrical. I had already discussed. It can be mechanical, can be on the daily and seasonal tracking. Usually we don't prefer it because we have to use additional motor to align our solar panel, and if the power consumed in that additional motor is not what we get from that system, it's not advisable. First thing. Second thing, with the passage of time, these moving systems may have rusting, may have a lot of problems. So to avoid those things, usually electrical tracking is preferred nowadays. Now, how it is done? We have these two curves. Maybe all of you are familiar with this. One we call a current with voltage for the solar photovoltaic system, and other is power with the voltage. So if we increase the voltage at this point, we call it's a zero current and the maximum voltage. So zero current means it's an open circuit. The voltage will be maximum. And at this, the zero voltage and maximum current, we can say short circuit. So between these 2 points, we draw at different solar irradiance. And these are the values. Usually in on the earth, we call 1000 watt or 1 kilowatt per meter square irradiance is equal to 1 sun. And we take it at that value. So this is the maximum value which we get. And if we see the power, because power is the product of voltage and current, so definitely here the voltage is zero and current is maximum. And at this point, the voltage is maximum, but current is zero. So it starts from zero and goes to this 0 point. And in between, somewhere it becomes maximum. This is the maximum power tracking. This is the maximum power path, depending on the solar irradiance value. So we have to track this path, this one. That means we have to operate at this knee point of this curve. Now, if you see here from this point, your system behaves like a constant current source. Here you can see the current is almost constant for different voltage values. And that's why solar photovoltaic systems are considered as a current source or constant current source. Normally, we say in definitions in electrical systems that a voltage source means whatever current you draw from it, its voltage must remain constant. And a current source we call whatever current value is there, the current value will be constant for whatever voltage you are having across its terminals. So here you can see up to this point, the current is almost constant, and that's why it is known as constant current source. Now, the second thing, when we want that it should be a maximum power tracking from this system, then we have to use a theorem in basic electrical. Usually we all have studied, that is maximum power transfer theorem. And in maximum power transfer theorem, what we say that maximum power can be transferred to the load if the load impedance becomes equal to the source impedance, or source impedance becomes equal to the load impedance. Now here in this case, source impedance is not changeable. You have a solar photovoltaic system, its impedance is fixed once it is designed. So what you can do, you can change the load impedance. And to change the load impedance, we have to change the system. Now, once a system is connected in between, load cannot be changed. Neither source can be changed, nor load can be changed. So how we can get it and how this maximum power point tracking does? For that, we introduce a DC-DC converter in between. And you know the DC-DC converter is considered as a DC transformer. And in transformer also we know that transformers can be used for impedance matching. That means if you change the turns ratio of the transformer, the impedance which is seen from input side or seen from the output side can change in the respective, you can say, turns ratio. Same way here in DC-DC converter, if we are changing the duty cycle of the operation, then the impedance seen by the source or by the load can be changed. And by this manner, we try to satisfy the maximum power transfer theorem. And once it is satisfied, the maximum power is automatically transferred to the load. So this is the basic concept of maximum power point tracking, which you all will be using. And for that, we change the voltage. How we change the impedance? Either we can change the current or we can change the voltage. So here we know that it's a constant current. We have to extract that much of current. So what we will change? We will change the voltage point. And that's why we shift this voltage point so that V divided by I changes and it matches with the load or matches with the source so that the maximum power is transferred. That is the basic fundamental of your maximum power point tracking. So I'll just go with the second system, that is wind energy conversion system, because these two systems are mostly used. So wind energy conversion system has wind axis turbine, wind turbines, and those wind turbines are defined in three different ways. One is called horizontal axis, other is called vertical axis, and then there can be conventional windmill, which may have inclined axis or it can have the vertical axis itself. Now, how it is done? I'll just try to give a picture of it. This is called horizontal axis turbine. We know that there are multiple big wind turbines. Is there any problem? Hello?
Participants, please mute your mic. I hope.
Okay. Someone has asked.
Ritu, please mute the mic of participants. I think they are disturbing.
Yes, sir, I have muted. Sir, I have muted them, sir. Sanjeev, sir, you can continue, sir. I have muted the mic of participants, sir.
Okay. Okay.
Yes,
So we have a horizontal axis turbine. This is almost known and seen by everyone. These are, we call grid connected commercial wind turbines. They are of this nature. It converts the linear motion of wind to rotational energy, and the basic principle is used like water turbines. Now, this is a vertical axis turbine. Maybe some has seen or not. It has a vertical axis and it rotates in the, you can say, on the plane. And it has a different kind of, you can say, power generation. So many of European community, they are using this kind of turbines, and it is known as C-shaped rotor blade turbines. And the advantage, if we see, of the vertical axis turbine is its generator and gearbox. It can be placed on the ground. If you see the horizontal axis turbine, all the generator and gearbox is placed on the top of that tower. So you have to lift it. It has to be kept there. Second, yaw mechanism is not required to turn the rotor against the wind. Like in the, you can say, this horizontal axis turbine, if there is very high wind speed, you have to convert your generator or your wind blades in such a way that gust of wind or that passes through it. So here it is not required. Okay. Disadvantage is that the wind speeds are very low close to the ground level, because wind speed is high at the higher levels. So very low power on the lower part of the rotor will be available. The overall efficiency of this vertical axis turbine is not impressive. And the name Darius machine used in it is not self-starting also. So needs a push to start. So these are the advantages and disadvantages. And usually we are going for horizontal axis turbines, not this vertical axis turbines. These are for small hillocks, and at some places in Europe it is visible, but not in Indian scenario, because we don't have such area here. This is one of the example. Now there are certain more examples for this vertical axis turbine, and this is to extract the small potential which is available at some small locations, or some location where the potential is very small. So these small turbines are being used, and one of the example I'll just show you this kind of example. This you might have trained, you might have seen in some of the commercials, where this looks like a tree, but it is having a very small vertical these turbines, and the cumulative power is good enough to light one small house at, you can say, very isolated location. So these things are being used. These are some improvisation and innovations, if you can see these things, and it is being used mostly in European part. So I just wanted to share. You can see its construction. It is having a kind of rotation, and these are wired. So all are connected, maybe series and parallel, to get your desired voltage and current levels. So that can be used, and it is being used. These are a few pictures you can see. And this one is the conventional one, which we call multi-blade type or sail type or dust type or the propeller type, which was used initially for some of the water pumping or some grinding mills. So these are also available. Conventional windmill, which are having multiple blades, and it is not of very high power range. So the vertical axis and the conventional mill, they are in the low power range. When we go for a high power range, definitely we have to go for the horizontal axis turbine, and that was the first one which I have shown you, this one. So this is very important, and here we can have very good blade height. Rotor diameter is very high. It can have a high power generation. It can be placed at the higher altitudes. Only the disadvantage is that we need a very high tower structure, and all the weight is to be kept on the top of the tower. So this is a inner view where you can have the conversion using gearbox and the controllers. So this is of mechanical interest. I'll not go into the details. Now comes the wind energy conversion system. Now wind energy conversion system, usually we say that whatever generators we are using in the wind energy conversion system, conventionally it is induction generators. And induction generator requires a reactive power. That means to establish its magnetic flux, it requires a reactive power. So that reactive power is basically drawn from the grid. So it has to be a grid connected. If it is a standalone, then definitely we should have some source to give this initial reactive power so that it becomes a generator. And then this AC-DC AC converter, which converts this system in such a way that the synchronization and voltage matching can be obtained from the AC side. So this is the basic thing which we use. Here also maximum power tracking is very important. So whatever available power, wind power is there, we have to go for the maximum power tracking in this case. So here we can say in the wind energy conversion system, R&D challenges are variable power generation, then selection of generator, matching of power demand and supply, then system behavior under sudden change, control of power flow, maximum power track. So these are the areas where the people can initiate their research. Now coming to a microgrid. It's a combination of electrical energy generation and the distribution system with solar photovoltaic, wind turbine, micro hydro. Then you can have geothermal source, thermoelectric generator, tidal, biomass, diesel generator, whatever it is. Here I have used this diesel generator because if you are having any standalone microgrid, then the basic source in case of no power is available from the renewable energy must be there, and that's why I have included this diesel generator, because still the diesel generator is the only source for power generation in remote and isolated areas where nothing is there. So we should have this component. It is very important that we should include this component, and we have to control in such a way that it should be operated when it is needed most and no other sources are available. So for microgrid, we have to check that diesel generator is a backup energy source only. Microgrid comprises of power converters, then battery energy storage if it is required, not necessarily, but if it is required, that is for the critical conditions. Then controllers and actuators and the protection system. These are the components. This is one of the example for the microgrid. Here I have used a diesel generator with a diesel engine. Then you can see there is a wind power, there is a solar photovoltaic, there is a battery, and we are having the connection. So we can have this wind, solar, battery, and diesel based microgrid system. And here the system is controlled in such a way that the maximum power point tracking is done with this converter for the solar photovoltaic. Maximum power point tracking of this wind turbine is done with this DC converter. And then at this DC link, we get, because here you can see that it is permanent magnet brushless DC generator with the wind turbine. So it is to be rectified. Then DC is connected with this DC link, and then this combined DC link is inverted to match the linear or non-linear load or the AC requirement. Diesel generator is connected for backup if any of these sources are not available. That is very important. It is a standalone kind of connector. So such configurations, if we see here, such configurations, what are the possibilities? Here we have seen for that configuration that we can have synchronous generator with the wind turbine, we can have a squirrel cage induction generator, we can have synchronous reactance generator, we can have permanent magnet synchronous generator or permanent magnet brushless DC generator or doubly fed induction generator. So these are the possibilities to which we can have a microgrid. And if this AC bus, if it is connected to the grid, then it will be a grid connected system. And if it is not connected to a grid, then it will be a isolated microgrid. So there are possibilities we can operate both of them. Now in this configuration, if you see, all these devices or all these generators are connected on the DC side. So there is no need of synchronization with the AC bus. There is only one inverter which synchronizes with this. So this inverter will have a larger rating. But if we are connecting these things, like here you can say that DFIG is connected on the AC side also. The stator of DFIG is connected because doubly fed induction generator, we are extracting its rotor power as well as the stator power. We can have both the sides. Rotor side can be controlled through this DC and stator power can be fed directly to this point. Here we need a synchronizer. So these kind of configurations can be used. This is on the basis of solar photovoltaic and the wind turbine. You can see here only two with the battery is connected. So we can have two sources based configuration. This is two sources based configuration. You can have even any other source also. This is solar photovoltaic and DC based configuration. These are all space and condition dependent. Like the situation, if the area where you want to connect this has good solar radiance throughout the year and good wind potential, then you can have solar with wind. If it is having only solar, there is no need to connect a wind because diesel is required in the night time. Suppose solar is not there and battery is not sufficient enough to supply the power, then definitely we need a diesel generator. So diesel is connected as a backup source for such a system. So it can be solar photovoltaic and DC based system. The machines can be these. I have taken these 6 types of machines in almost all the configurations. You can have even other. These are why we are having these ones. If you just see here, this PMBL DCG, PMSG, SCIG, SYRG. These are all we call brushless generators. Here, no brushes are required. But if you are having a synchronous generator or if you are having a DFIG, it will require brushes on the rotor. So if you want that there should be low maintenance requirements, you have to go with these brushless generators. That's why I have given different types of configurations. Then we can have solar photovoltaic and micro hydropower. Here you can have micro hydropower. Rotating part will have these generators and then the PV is connected with them. We can have different combination of 3. Previous one were 2 source generators. Now we can have 3. If we have solar, wind, as well as the say some river is there, so we can extract all the 3 and we can have a connection of all these 3 with a combined microgrid. So this configuration can be used. In this configuration also, the control is very important. Then we can have solar, DG, and micro hydro, solar, DG with wind turbine, or we can have all the four: solar, DG, wind turbine, micro hydro power. So the combination can be different. It depends on the availability of the systems, availability of resources. But as you increase the number of sources, your control complexity increases, because control complexity is directly dependent on these factors. So you have to just think on the control complexity also, as well as the availability of power through the resources, and then its cost benefit analysis. Suppose you are having one source which is available for only 2 months, and the costing is too high to add that source, then it is not advisable to add that source in your microgrid. That is very important, that what kind of system you are having there and how much its cost benefit analysis, or you can say economic analysis, gives you the return. Because power production is important from the cost point of view. But if the location is in such a way that the other things are not available, it has to be a standalone system, you don't have anything, definitely you can go for it, because creating infrastructure or creating a transmission line to make it a grid connected one, it will take lot of investment, and it can be avoided. But in the other way, if you see, the power is available in abundance, lot of power is available, and that can be fed to the grid, then definitely one should go for a grid connected system, so that the power, because that power requirement at that remote location is small and the power availability is larger, it can be transmitted to the places where it is required. So those feasibilities or feasibility studies are also very important. So some of the researchers are actually doing on the feasibility study also economics of these configurations. Now, we have to control all these things, and definitely it has to be coordinated. How it can be a coordinated control, that is very important. So in renewable energy sources based systems, additional power converters and energy storage are required for power balance in the system during load and weather perturbations. Perturbation means you have to change the load, or if the weather is changing, if the load is changing and the weather is changing, how your system will behave. Even then, the uncertainty of power may require DG for backup. That is very important thing. You cannot avoid the power outage through renewable energy sources, because there may be some abrupt situations, and if there is a critical load, like if you are having say one hospital connected to it, where the life support system is there, or if there is a data center. Someone has kept his mic on, please mute it. So if there is a data center, or if there is any kind of communication system like a telephone tower or internet connectivity issue, you have to keep it on for all this time. And if there is no resources of renewable energy, definitely you have to go for a DC power. So that is very important. And you have to decide a coordinated control strategy. That's why it is written here that a coordinated control strategy is required for operation of such renewable energy system based microgrids. That's very important. Now, the coordinated control strategy must incorporate the following: synchronization, power quality improvement, efficient operation at light loads, optimum operation of all the generation resources. You have to optimize it, you have to prioritize it. Then the power balance in the system in presence of perturbations. That is very important. So these are, we can say, the objectives of the coordinated control strategy. There may be many more, but these are the essential objectives of a coordinated control strategy which you are going to design, and how it is considered. Like if I say that there is a condition where the power which is demanded from I can say PV, wind turbine, DG, combined power is less than the load power, then because we are having these things and load power is even higher, we are having energy storage or energy sources like wind turbine, solar photovoltaic and DG, then we have to supply the deficit power from the battery energy stores. That means the battery will be discharging. So we have to give a strategy where this power will be compared, added and compared every time. So the sensors are required very much there. Then if we have these three powers, which is greater than the load power, that means the demand is less than the generated power, the excess power will be going for the charging of the battery energy system. These are the conditions when the SOC, state of charge of battery, is less than 100%. That means it accommodates the extra power. But if SOC is equal to 100%, suppose the battery is fully charged, then even if the power is higher or equal, then at that moment we cannot feed the power to the battery. So we have to stop charging. Now under this condition, what should be done? So there is a term you will see in literature, they call it dump load. There is some kind of load connected to the system which we call dump load, and those dump loads are turned on under this condition. When your battery is fully charged, the generated power is higher than the load demand, and usually those dump loads are in heaters. We call the heat generation units in cold countries like Europe and Australia, America, Canada. And in Indian system or in the areas where heat is not desired, but cooling is desired. So what we do, we store it in a cooling system. If anyone has visited AIIMS Bhopal, can see in AIIMS Bhopal that for such a situation, they are having a cold storage units. They cool it. They are having some of the big containers in which chemicals are there and they cool it. And whenever there is a power cut, they pass either air or the water to extract that cooling so that the air conditioned areas can be maintained. So that kind of thing can be done. And these systems are considered as dump load. The second thing which is used, we call that prioritizing the load. In Indian system, we are not having the time of the day tariff. That means at the time when the demand is too high, your tariff increases. In European community or in this American continent, what they do, as the demand increases, your power price increases. Like in the demand period, high demand period, the power price may go double and triple of the original price. And when there is a deficit of demand, that means there is no demand, at that time they give very cheap price. Sometimes the negative pricing is also done. That means if you use at that moment, your energy bill will actually reduce. So that kind of pricing is done, and on that basis, the loads are prioritized. For example, in our household applications, we are having certain loads which are not very essential, like washing machines. Like you can have, say, if you are having dishwashers, or if you are having some kind of electrical cooking devices. Suppose you get a chance that at around say 11 o'clock in the morning, at 11 to 12, you get a cheaper electricity price. You can operate at that moment, or in the afternoons at somewhere 2 to 5, if you get a cheaper price, or in the nights, like after 10 or 11 in the night, if you get a cheaper price, you can operate all these things. They can be programmed. These things are being practiced, and they are even governed by, you can say, IoT, Internet of Things. You can make a programmable things so that they are being operated at those periods when your power is very much cheaper. And there these conditions can be given, which we are discussing here. That if the power is in excess and there is a cost, less cost of that power, then we can turn on those applications. And these things are considered as a demand side management. So you might have studied about this demand side management, but this strategy can be used for the control, or because we call coordinated control strategy under the microgrids. So this type of definitions or this type of rules can be defined. Now, how it is done, just a block diagram I had given, that for maximum power point tracking, which we have seen earlier in our discussion for a solar photovoltaic array, suppose load is connected here, we sense its voltage, then we give a reference voltage based on our characteristic of that solar photovoltaic, that what should be the voltage level, so that from solar photovoltaic we can extract maximum load. Here you can see that this load is having some impedance, and this side will be considered as the internal impedance. So this internal impedance will be converted to the desired value by the duty ratio of this DC-DC converter. So if we can control this DC-DC converter switching, then we can have maximum power point tracking. And by this, we just check the control, what is the error, and then accordingly we control the switching, and so that this scheme is done. So this is one of the control. Okay. Now in this one, we have used very simple PI controller, and the PI controller works on the basic principle of this formula. And then we have a current controller, that how the current will be actually checked if the error is greater than a signal, which is we call sawtooth. Here I'll just show this one. We have a high frequency sawtooth carrier, and this error is compared with this one. So we can give the formula here, like in this one, whenever you see that the error is less than this sawtooth, your switch is on. And as the error is increasing, your switch is becoming less, giving the less duty ratio. This can be reversed also. If we just reverse it, then this part will invert. That means this will go on the top, and here it will become off. It depends on what kind of application you are using. Suppose increasing error requires more turn on of the switch, then this will be inverted. This scheme which I am showing should be inverted. But if increasing error requires less turn on of the switch, then this scheme will be workable. So it depends. You can have the formula which is given here in the previous slide, that if error is greater than this, or if error is less than this, switch is on or off. This you can check, or you can decide. Here you can give different rules. So this will be changed. The second thing, in some of the PWM controllers, you might have seen a triangular waveform like this one, from this point to this point, not this sawtooth one. If there is a triangular waveform, you can see that your PWM will be symmetrical about this axis, means its midpoint. If this is a triangular one, maybe I have not, okay, I have not taken this one. Just I want to discuss that if this point is connected with this like a triangular waveform, then the output will be on both the sides, and its frequency will not be constant when the error changes, because symmetry of this waveform will be across this peak point, and it will increase and decrease on the both sides. So the frequency will change. But if you are having a sawtooth waveform, then the frequency is bound to close at this point, whatever turn on time is there. So this scheme is used for a constant frequency PWM. This is very important. And as you know, there are two devices which we use in these controllers. One is IGBT and other is MOSFET. IGBT can operate at lesser frequency maximum up to 20 kilohertz with high power range, but the MOSFET can operate at higher frequency but low power range. So it is up to you that which device you want, because if you are using a variable frequency in IGBT and suppose it goes beyond 20 kilohertz, then it will become a short circuit and it will damage your device or your converter, inverter, whatever you are using. So to have that distinction, you must know that where to use which PWM controller. That is very important. And this is what we have discussed earlier, that we need this point, that is the maximum power point. So I'll just discuss, because one of my paper is on this issue, that here you can see this curve is a little bit parabolic in nature. It is a little bit having a curve, this maximum power point, if we start from it. But if you draw a straight line, this point will be a little bit left or right. So you can draw a straight line, and if you can fix a constant voltage switching, even then you can get a maximum power tracking in a solar photovoltaic system. And that too without any MPPT controller, maximum power point tracking controller. So sometimes what happens in some of the research, people say that reduce the number of sensors, reduce the number of controllers to make the system simpler. So that can be done. So from visualizing these curves, you can do something different, whatever is being done in the literature. So that was my intention, that if we put a straight line from this point at this say 30, then you will see that all the points either they fall on line or it will be left or right, minor left or right. So with the minor compromise, you can get a maximum power point tracking without any tracker, if you fix your voltage to that particular voltage. Okay. So here you can see in the MPPT algorithm, what we do basically, we input the voltage of the photovoltaic, current of the photovoltaic, then based on this algorithm, we select that what should be the current from the MPPT and what is the load current accordingly. If there is error, the PI is giving us that particular voltage, what should be the operating voltage at which this maximum power point tracking is required, then what is the voltage of VPV, and then we try to get a particular voltage with that ratio, that what should be its duty ratio for your system. So that is being used in solar photovoltaic. You can have many other things. Only what you change is this MPPT algorithm, like you go for the perturb and observe, or you can go for the hill climbing method, or you can go incremental conductance, or if you have any new method, you can go for the new method also. So this is what I was telling, that if you fix a voltage, constant voltage, you can remove that MPPT algorithm. Here you can see that at constant voltage, almost we get a maximum power. Here it is little bit on this side, but it doesn't matter. If you are removing, if the cost of controller and complexity of that consumption is reduced, then it is worth to have a constant voltage operation. But you have to just check it whether it's required or not. Then for the wind turbine also, we can have an MPPT control algorithm in which these signals are being used. This is from one of my paper. Now here we have used one AWPI, that is called anti-wind-up proportional integral controller. Because in proportional integral controller, there is a problem of saturation. If it operates for longer error, then it saturates and it never changes suddenly. Suppose your error is very high, then PI will take a longer time to control the system if it is not tuned properly, or even if it is tuned for, say, steady state conditions where your error is very small. Now, if there is a transient condition where the error is large, then it will go into saturation. And for that, we need an anti-wind-up algorithm. And that anti-wind-up algorithm, it actually reduces sample to sample those saturation errors. So your system becomes faster. So that is also very important for anti-wind-up system. Same system can be used for the battery energy storage. Here also, if you are having larger errors, then anti-wind-up is very much required. And we have to see that what is the requirement of battery, what is the state of charge. Because if battery is full, we cannot charge it, because overcharging will lead to loss of the battery. Battery may get damaged. So here it is very important to have a coordination in the control for battery charging as well. Then the voltage source converter, that voltage source converter which is feeding the complete power to the grid side or to the load side, because we are connecting all our resources on the DC side and only one voltage source converter is there, or we can say inverter is there. So if we are going for that inverter, definitely its control is very important from loading point of view and from the, you can say, frequency and voltage regulation point of view. Here also we have used anti-wind-up, but this PR we have used proportional resonant controller. This resonant controller is introduced in this paper specifically to have the specific voltage and frequency control, so that it can be controlled quickly. That if there is any change in the generation, then or any change in the load, it can be controlled quickly. So you can just see these things. I'll not go into the details of these equations. These are simple equations for the three-phase. And this is how the voltage frequency regulation is there. It uses the vector control principle, where we are having ABC to DQ control. That means stationary reference frame control. I'll just give a basic idea of this vector control. Maybe all of you are aware that the three-phase system, we consider that there is a plane which we call phasor plane, and there are three phasors A, B, and C, which are 120 degree apart from each other, and they are rotating at a frequency omega. So they maintain this 120 degree with respect to each other. Now, when we go for a vector control, usually in vector control, we say that we go with the rotating reference frame. Now, what is the rotating reference frame? There are three reference frames which we are going. One is called stator reference frame, other is called air gap reference frame, and third is the rotor reference frame. So why it is needed? Usually what we say that whenever there is a stationary plane and the phasors are rotating, to calculate exactly how much is requirement or where the phasor is, it is very difficult because it's a rotating system. So in a rotating system, controlling the parameters like voltage and frequency or voltage, current, these things, it is very difficult because you have to estimate, then control. And during this, there will be a delay. This delay may lead to the errors. So people thought of that if we make the reference frame rotating, then the system will be stationary. Like you see, a frame is stationary and we are rotating, or we say that those vectors are stationary and frame is rotating. So almost it will be a similar thing. But to convert it, we have used these two coordinate transformation, ABC to alpha beta and then alpha beta to DQ, which we call as Clark and Park transform. Now what we do, initially we assume that ABC, these are three vectors which are rotating on a stationary frame. Then we convert these three-phase rotating to two-phase rotating, alpha and beta, which are 90 degrees to each other. Still, the frame is stationary. That means the phasor is stationary. The background is stationary, and these phasors, two phasors are rotating. And in the second transformation, where we call alpha beta to DQ, we say that the vectors are stationary, now the frame is rotating. And that frame rotates at the same frequency, which is its reference frame. Like if we are taking a stator reference frame, So we assume that stator magnetic field is rotating at the synchronous frequency. So we rotate that frame at synchronous frequency so that those two D and Q axis components of voltage or current, they are stationary. Now, if anything is stationary, I know that how much is my requirement. I have to just adjust those two things because my frame is rotating at synchronous speed. I don't bother about those frames. And that is what the vector control is. Basically, vector control makes your system easier. And if you are having only two, which are decoupled one, we call D and Q axis. D axis is the direct axis, which is representing your magnetic component, and Q axis is representing the torque component in the machines. We know that these two, if we control, if we have to make torque variable with a constant speed, we have to keep the D axis constant and the Q axis will vary. Or if you want the torque constant and if you want that speed should be variable, we will keep Q constant and D will be variable, and accordingly we will reverse it DQ to ABC, and then finally we know that how much is my requirement. So that way this vector control has simplified. But during this simplification, a lot of conversion is required and control complexity increases. So we have to just work on that. And this is all about those control complexities. So here we have VABC, IABC, and this side we convert it again and then try to get the gate signals for the voltage and frequency regulation. Hope this is clear to you up to some extent. Now this is a diesel generator control scheme. In the diesel generator control scheme, you can see here we have given 2-3 conditions: load power, then renewable energy power, then SOC, state of charge of the battery. These three are inputs, and this is the condition. If load power is greater than the renewable energy and SOC is less than 50%, what should be there? So there are conditions, and based on those conditions, the DG is turned on or off. Where the charging is required or where the discharging is required, the battery is turned on and off based on these parameters. Whether the solar is available or not, the wind is available or not. We can introduce even further things in this coordinated control scheme. Suppose solar photovoltaic has lower cost of generation as compared to the wind turbine or wind power. So what we can do, we can even prioritize. Sometimes there are people who are prioritizing, although we say that it should be a maximum power extraction, but we can prioritize that which power should be used at the most for that particular area. And that can be done at the beginning stage. That means at the design stage itself, if you know that at a particular place, wind power will be more costlier than the solar power, we should introduce the solar plants more in number in comparison to the wind plants. We should avoid the wind plants. But if it is required, urgently required, or just to have some extraction, we can go for that. So those things can also be included in the coordinated control scheme. This is for the wind turbine control scheme. Here we sense the wind turbine power, and then accordingly for the maximum power tracking, give this boost converter the switching signal based on the scheme which is designed here. So designing this scheme is altogether the you can say designer's consent or designer's discretion, or the person who is doing it. So this can be changed. Here we are using one scheme, you can have another scheme. So whosoever is doing the research in this area, they have to do this kind of design equations. They have to run these design equations, and they have to compare with the established schemes or established reported literature so that they can show that my controller is better in the situation which is arising at particular place, and it gives a better solution as compared to the solution available in the literature. That is most important. Then you can have MPPT scheme. Here this case at new, if you see, this is for the sliding mode controller. Sometimes we use different controllers. So if you are using a sliding mode control, you can have such kind of control in between. This is in series with the P&O, perturb and observe. So if you know that perturb and observe is having a disadvantage that it increases chattering. That means there is a, I can say, variation of voltage, very fast variation of voltage if this scheme is not designed properly. So to avoid that, some other schemes are introduced, and in that effort we have used this one. But this has also, this is having the disadvantage that it also has some chattering. So sometimes what happens in a particular scenario, some combination gives a better result as compared to the other one. So we have that kind of publication, but it is not a universal solution. You can have different solutions also. This is for voltage and frequency regulation, same as the previous one, where this K sigma, this nu is used as a sliding mode controller in between. These are the microgrid configuration based on the photovoltaic and wind turbine, which I have shown you earlier. And the PV array data is there, DC-DC boost converter data is there, wind turbine data is there, the PMBL DC data is there. All these data is given here, and this is for DG based wind turbine. So you have to show that what is your data, what data you are using. And this is a laboratory prototype which has been used for a microgrid. Here you can see many components. This is a solar simulator at serial number 5. You can see here. This is generator motor combination representing your wind turbine. This is 1 and 2. This is a combination which is representing the diesel generator. Then if you can see here, these are the batteries. These are the batteries kept. So this is a battery bank. Okay. And this is a transformer in between connected. This is the inverter which is connected to it. And then the controller is on this. This is called D-space. We have used D-space board here. So these controllers are being used, and this microgrid simulation and hardware implementation, these are certain results. In almost all results, we have to show some kind of perturbation. That is very important. Here you can see that as the wind turbine is increasing, that means wind current is increasing, the battery immediately goes down. This is the zero line. So battery was initially supplying and then it has gone into the charging mode. That means it's a coordinated control. We have to prove it that how our system is coordinated. You can see here that the photovoltaic is having a constant one, but the wind turbine current as it has increased. Here you can see as it has decreased, this has increased, this battery. Okay. Here you can see the same. If wind turbine current is constant and photovoltaic is reducing, the battery has increased its current. Or the second one. Okay, here you can see the results. We have taken 2 phases because it was a 4-channel digital storage oscilloscope. So 2 current channels and 2 voltage channels we have taken. We have not taken all the 3 channels. Here we have shown that if one load is off, that is unbalancing of load. You can see with a minor perturbation at this point, almost the voltage is being balanced. Here also, if both are off, even then your voltage is not disturbed. These are the things which you have to show in your results. That if my load is turned on or load is turned off, even then the voltage supply is not disturbing. Because if it is disturbing, it will certainly impact the other appliances. So it will change the power quality or it will change your set points. So these are the results which we can show. Dynamic performance at PCC, you can see here that inverter current, how the current is changing and then it is managing. Here you can see the load current. One phase has increased current. Here you can see the inverter current has increased for that particular and then it has managed, it has maintained. Here you can see the DG has at this point, the DG is having lower current than it has increased. That means it has started supplying the increase in the current. Here you can see the inverter current is disturbed. Why it is disturbed? Because load current, one phase has a disturbed current. That means unbalance of current is introduced, but the DC has supplied the current in a, you can say, voltage and current. You can see it's in a balanced manner. It is not unbalanced one. Although the inverter is having unbalanced current because the load is having unbalanced current, but the DC is supplying the constant current. Here you can see the voltages. So these are the things which you have to represent. Even if you're, you can say the drastic change here. Here a small change, here a big change. Even then you can see that DC and a reference, how they are coordinating each other. They are trying to control each other. Here you can see the current of the battery and the reference. They are matching with them. Here you can see in between. Okay. These are the variations. Wind turbine is having permanent magnet brushless DC generator. So you can see these are having a trapezoidal kind of voltages and currents. You can see here. So these values are there. So these things you have to just show. Okay. The total harmonic distortion you can see here. Harmonic load current was having 14.5% harmonic. The DC current was having 2.14. And the voltage at PCC, point of common coupling, it was having 2.35. That means these two are unaffected by the load harmonics. That is how you have to go for the controllers. That means it is giving you a coordinated control in the variable environment. And that is most important thing which has to be taken care of whenever you are going for a microgrid control. So in conclusion, we can say that the microgrid configurations are designed according to available renewable energy systems in that particular region. The coordinated control strategy for microgrid system can be designed to suit the local requirements. That whatever the local requirement is there and whatever local availability is there of renewable energy sources, based on that, you can design a coordinated control strategy. The performance of 3 energy source based design has been presented for successful operation in this work. And this configuration has a reduced number of power converters to make it a low cost option. Why we call that low power converters are there? Because we have connected all the sources on DC side. So that the power converter which we are using as a main power converter is a single one, and that does not require any kind of synchronization. Because synchronization is a biggest problem when you are having variable generation or distributed generation. So to avoid that, this low cost option was supported in a microgrid environment. And the results shown are given for the good performance under different linear, non-linear conditions, load balance and imbalance conditions. So this is all from my side, and if anyone is interested, this reference, the first reference which we are having, this is one of my paper published in March 2019, microgrid configuration, control and applications. There you will get all the details, and related to that, if you want a specific one, then this second paper you can see the wind PV diesel based standalone microgrid, and there are many other papers also which are related to this. So you can just go through those papers, and it is very important that whenever you are going for such system, you have to be very sure that your system must operate in a coordinated strategy with the desired outputs. And just to inform the student that if you want that these research should be published in IEEE transactions, you must concentrate on hardware implementation. Many of students, they say that it is very difficult to publish papers in IEEE transactions. But my personal experience is that if you have hardware implementation in your laboratory, although it is a very small one, definitely your chances increase a lot. So whosoever is working, do not concentrate more on only software part or only I can say simulation part. Try at least one small hardware. Once the hardware is installed or hardware is giving you the results, your paper can be converted to a IEEE transaction, because the people who are publishing in IEEE, they are from the same earth, from the same area, from your vicinity nearby. So do not think that they are very great people or something like that. They are amongst you. Only you have to explore your potential through hardware implementation. And most probably, I know that Dr. Bhupen Singh is having a very good lab in RGPV. So if anyone is interested, he can even go for those systems. There also you can have your hardware implemented. So this is all from my side, and if there is any query from anyone, you may ask, please.
Thank you, sir, for the detailed explanation. And sir, I would like the participants, who anyone is having any queries, kindly you can open, unmute yourself
Anyone wish to ask
and
any
ask.
question?
Now you can unmute yourself, and if you have any doubt or queries, please ask to sir.
Thank you very much, sir. Professor Sanjeev Singh, sir.
Most welcome.
Any queries from participants?
Okay, if they are having any query, they can mail me at my mail ID, official mail ID. They can mail.
Now I would
Sir, just a minute. Sir,
Sir, I have unmuted everybody.
Yes,
Hello.
somebody's asking.
Hello.
Sir, I have
You
unmuted
can ask
everybody
please
now.
question. Now
Yeah,
you can unmute yourself. We have allowed you to unmute your mics. Please ask questions.
Sir, Shalu this side from Galgotias College, Greater Noida. Actually, I just want to ask that in one of your slides you have mentioned by changing the irradiance of a solar panel, that is actually a competency, or we can say a problem associated with the solar panel. So if I'm changing the irradiance of different cells, there are number of peaks I'm getting in a PV and a IV curve. I just want to know that how I'm going to like check or verify that different peaks, like where it is situated. Like the highest peak, if it is at 2 milliampere or 2 ampere, then it comes at 1.5 milliampere. If I'm saying for the IV curve, so how I'm going to say ki if the irradiance is 300 meters, if the irradiance is 300, then it is getting the peak at 3 milliampere, and if I'm changing the irradiance 500, then I'm getting the peak at 5 milliampere. So how I'm going to distinguish it? Because I'm actually changing irradiance with a different irradiance at a single solar panel.
You are measuring. It is about your simulation model. You are talking about simulation model.
Yes, now only I'm working on simulation only.
Okay. So what you have to do, first, whatever model you are using, because in simulation you might be using some preset model of solar photovoltaic.
Yes, sir.
So check the characteristic of that solar photovoltaic at different irradiation level.
Okay, sir.
Okay.
I
Yes,
think
sir.
madam is having a problem for the partial shading condition. I think so. She's for different irradiation. That is the thing, ma'am.
Yes, mom, actually.
No, if
Irradiance,
it
if
is a
I'm
partial
changing.
shading condition, then the system will be different.
Yes, sir. If I'm changing the irradiance, that means some partial shading will occur.
Okay, partial shading. See, partial shading means your complete solar panel is not subjected to the desired solar irradiance. So partial
Yes.
shading problem is altogether different. I have not covered that area in this one.
Okay.
Partial shading has to be taken separately.
Okay. Okay.
For
Sir.
partial shading, you have to see the characteristic of your system. You have to first test your system that in which area, if I'm using partial shading, then what kind of characteristic it is giving. And to check these partial shading conditions, you have to make your own algorithm that it is having a partial shading problem, and then how to tackle these partial shading problem. The algorithm shall be a different one.
Okay, sir.
I'm talking about the maximum power point tracking, because in this condition, we are just thinking that the power should be maximized depending on the required controller configuration. And then according to that, we have to extract the maximum power. So I have not covered this partial shading.
Okay, sir. Okay, sir. No. Thank you so much.
Any other queries?
I think so, sir. There are no other queries. Sir, may I now request Bhupen Singh sir to Bhupen Singh sir? Bhupen.
Now we can close the session, I hope.
Hello, sir.
Yes, yes.
Sir, actually the net was gone. That is why
Yes, yes. Okay.
we
can
we
close
were
the
not
session.
able to stop.
Okay, so on the
Thank you
behalf
so
of
much,
the
sir.
entire electrical engineering department, we are very much thankful to Sanjeev Singh sir. Thank you very much, sir, for giving us insight on the solar and wind MPPT techniques. Definitely, we will be greatly benefited by your lecture. Thanks a lot, sir.
Thank you very much. Most welcome. Okay, I take leave.
Thank you,
Please
sir.
take
And sir,
care.
we
Bye-bye.
look for in future also. We look for your lectures, sir. Hope you will surely come and
Sure, sure.
take
Thank you.
lectures. Thank you so much, sir. Good day, sir.
So, dear participants, we are having another lecture at 5:30 p.m. today.
Yes, Sanjeev sir has left because my power just got disconnected. Is he here?
No, sir. Just left.
अच्छा, उसी वक्त मेरा पावर जो है वो चला गया and I was not able to thank him.
Sir.
Sir has left. Sir has left.
Yes.
Yes,
Yes, sir. I think so. Sir has left, sir.
Okay, I will talk to him personally. Please inform